Welcome. Today we're going to be talking about Taylor series for functions of a complex variable. So let's first write down what the theorem is. So we're talking again about functions. Oops. F of z that are analytic. F is analytic in some neighborhood of z naught, which we'll say is of radius r0. So I have this point right there, and there's a z naught right there. Okay, so so basically we can write a z as any kind of number, any complex number that is somewhere inside of there, and then we have that there. We have that radius r0, and the radius of z, we'll call that radius then r. Okay. So for any z inside of here, we can write that. I'm going to do a few more little pieces of a notation here. I'm going to make this outer edge here. We're going to say that that the function is analytic in some neighborhood and on the boundary contour C0. So I'm going to call that C0. Okay, so it's going to be analytic a little bit outside of that region there. Okay, so that just helps with some of the utility of proving this theorem. So if this is true, if f is analytic, then we can write down the following statement. We can say now represent, f can be represented as a power series of the form sum from n equals 0 to infinity of an, where those are complex numbers, times z minus z naught to the n power. Okay, where an is equal to the nth derivative evaluated at z0 all over n factorial. And of course, this is just like for f of x, where that's a real variable. Okay. So this is exactly the same statement as Taylor series for functions of a real variable. And what we're basically saying here is analyticity, i.e., which in this case means that all derivatives exist in this neighborhood in a region around z naught, okay, which we'll call D. So D, we'll say, is this whole thing that includes this contour C0 and everything interior to it. Okay, and so analyticity buys you that infinite differentiability, in which case now what we can think of, so let's take a step back here and just get an idea of what this means. So analyticity of f of z, i.e. it has all these derivatives, I can represent f by knowing z0. I'm just going to skip that, by the data. I'm going to call it data just to really affirm what this is talking about. The data, these complex numbers an, which form a sequence starting at 0. So it's an infinite sequence, but the thing to note is it's discrete. Okay, it's a countably infinite set of numbers. So if I have this data set here, this list of numbers, then that data fully determines f of z near z naught. Okay, so that's a really powerful theorem, and of course it should be noted, I just kind of put in a bullet point, that Taylor's theorem is used in many numerical schemes, solution schemes. So it's of fundamental importance for applied mathematics. So, for instance, solving ordinary differential equations, things like Runge-Kutta, and many other numerical schemes utilize Taylor's theorems in order to approximate functions. So, it's used as a way of approximating function f of z by polynomials. So, you probably spent most of your life in math, learning math, and studying polynomials. And now we have this really great theorem that says that if you have a function that's infinitely differentiable, i.e. it's a very smooth function, then a polynomial can approximate that function. So polynomials are very special in that they can, any differentiable function, they can approximate really well. And so that is one of the big uses of it. So polynomials are, of course, very easy to deal with. They're very, they're functions involving powers of z with some constants, some sort of coefficients. And those coefficients, this discrete set of coefficients, then fully determines what f of z is. And we can think of this as the information, the data, if you will, that defines a function. And the fact that it's a discrete set, I think, is very interesting. And so let's just contrast to non-analytic functions. So what we're talking about is some general function without any special relationships or derivatives or anything like that. So in general, f of z, if it's just some arbitrary function, that means that it's an input-output relationship, where if I have a point z and then it maps to a point w in the plane, that this, these pairs, zw pairs, define the function. And what we want to note from this is that those pairs are, of course, not discrete. If this is a function where I can input in some complex numbers and I'm outputting out some complex numbers, the mapping between z to w, that's not a discrete set. It's actually a continuum. It's an open set, not discrete. Sorry, I'm not spelling very well today. So not discrete. It's an open set, and the real big point here is that knowledge of one z1 and a w1 pair does not, in general, tell much about f. In order to understand what f is, you have to have all the pairs, which are a not discrete set. But now, if f of z is analytic in some domain, the data that describes this function can be written down as an ordered list of coefficients, and that fully defines the function. And so, of course, this is a much smaller set. Okay, even though it's an infinite set, it's not an open set. It's not a continuum of points. It's a discrete set of points. And so that that sort of data reduction, if you will, is sort of like, you can think of it like a data compression. That's one way to think of it. Now you've taken it down to something tractable. And now if I take a truncation, if I just take a finite number of these points that stops at some capital N, I could store this on a flash drive. I can send it to a friend. I can send it. This is a finite set of numbers. I can store in a computer. I can send across the internet, and then someone can recreate. Later on, you can recreate. An approximate f of z at some other later date, and you can get it to any resolution you like, because you can simply take more n values to do a better and better approximation. So that's a really nice feature of the Taylor's theorem, is the idea that the information about a function can be stored in some discrete list. But in general, for some general function, of course, that's not possible. We can't, in general, do that for every function. But now we have this really nice way of thinking about functions. So that's the way I want you guys to think about what f of z is saying and what the Taylor's theorem is saying. So let's actually just get to proving Taylor's theorem. I think this is a really good one to prove. It's so fundamental for everything that we do in applied mathematics. It's worth going through the proof. And I'm not going to really set this up as a proof. It's actually more of a direct calculation. And we're going to use a couple factors. One, we're going to use the Cauchy integral formula, which is that if f of z is analytic, we can write some contour, and I'll take that contour C0. I'm going to recreate that there. There's our contour C0, and we have some domain that C0 fits in. And I'm going to take my z to be inside of that. There's my z, and there's z0. It's centered at z0. Okay, and this is going to be, again, radius r0, and that's going to be radius r. And I can write it as this. So we're going to use the Cauchy integral formula, which we've already proven. So this is going to be s minus z dz. So we're going to think of z as being a fixed value, but then it's arbitrary. I can pick any z in the plane. I can pick any of these z's here. But so one thing to note is s, of course, is we're integrating over this contour, so s is always going to be on this contour C0. And that'll go around. So it always has a fixed radius r0. And of course, z will always be inside. It'll be interior to that point. So we're going to use that Cauchy integral formula and the extension. So we can write the derivative, the nth derivative of z, as n factorial over 2 pi I integral over C0 of f of s all over s minus z to the n plus 1 power. Oh, sorry, this should have been a ds. Okay. So clearly you can see already I'm actually going to divide that through and put that down there. That'll be my n factorial. Okay, we can already see that this, this looks like the coefficient. Looks like the coefficient an. Okay, so we already have a bulk of the theorem proven. All we have to really do is learn how to put it together. And to do that, what we have to do is recall the last piece of the ingredient. I'm going to call this is 1, and that's 2. So Cauchy integral formula and its extension. And finally 3. The last useful piece of information is that of a geometric series. And that geometric series, we can write it as follows. I'm going to go n is equal to 0 all the way to infinity of some complex number w to the nth power. And we found that it is equal to 1 over 1 minus w if the modulus of w is less than 1. Okay, so that's a very important piece of information. But I'm actually going to rewrite this another way. We've learned from before that in proving that this theorem was correct, I'm going to rewrite it in the following way: that this this sum n equals 0 to infinity of w to the n power is equal to, I can write this as 1 minus 1 minus w. And then I can have a sorry, I kind of got a little lost here. So we can rewrite this as, we can add to it a plus w to the n power minus 1 minus w, and then a subtraction of w to the n power 1 minus w. And it turns out, of course, that if you rewrite this as 1 minus w to the n, 1 minus w, plus w to the n, 1 minus w, this term right there, that's actually equal to the finite sum, from n, capital N minus 1, from little n, 0, of w to the n, plus, and then we put that one down there again, w to the capital N of 1 minus w. Okay, so that's just another way of writing this, this same infinite series. And so this is going to be able to buy us a great deal. So here are the three ingredients that we're going to use. Okay, and again, we're going to have this, we're always going to be talking about a z point that's inside this contour. And we're going to be doing, and we're going to always start with here. Here's our representation of f, and f is actually written like that. You can already see there's a z, s minus z in there. And we're going to make it look a little like our geometric series. So we're going to, when we see something like this, we're going to put this in its place. Well, actually, we're going to put this in its place. And we're going to see if we can calculate this integral over this sum. All right, so now we see we have all the pieces put together. So let's just do this. Unfortunately, I'm going to have to move to another page, and I'm going to have to rewrite some of this stuff. Okay, so let's talk about that. I'm going to put this up in this corner again. We have our c, c naught, and then we have our z, and our z naught, and that's going to be radius r, and the radius of this c naught will be r0. Okay, so there's that. And again, we're going to start with the Cauchy integral formula, which is f of z is equal to 1 over 2 pi I integral over c naught of f of s minus s all over s minus z ds. Okay. So the first thing we're going to do is take this, and this looks a little like our geometric series. I'm going to rewrite it as follows. I'm going to factor out an s, and then we get a 1 minus z over s. Okay, that looks good. All right, so now this looks a lot like a geometric series, so I'm going to rewrite that again. And then we have a sum, and now we're going to go from n equals 0 all the way to capital N minus 1 of z over s, that quantity, to the little n power. And notice that because s, remember the magnitude of s is going to be r0, and the magnitude of z is going to be r, it implies then that z over s, the magnitude of that, the modulus, is going to be less than 1. So of course that satisfies our condition for convergence of this series, of these partial sums as capital N goes to infinity. And then we're going to do this plus z minus s. So we're going to put that all in a big parenthesis to the capital N power all over 1 minus z over s. Okay, so that looks good. So now I'm going to plug all this in to this over here, okay? And we're going to get, so again, f of z is now equal to 1 over 2 pi I integral over c naught. And then what we're going to do is, I have here a sum, n equals 0 to capital N minus 1. And then we have that z to the little n there. And then what we have there in the denominator, I'm going to put a s to the n plus 1. And again, we have to put this f of s there, so that'll become an f of s. Okay? Right, so there's our finite sum there. And then we have to go to this term here. Again, we see a z to the capital N all over f of s, and I'm gonna call that ds there, right? I'm gonna put another integral, so I'm just gonna move the integral through all that, all over, and then we have an s to the n. Oh, we also have to put the actually it's going to be a and then I'm going to distribute this s in, and I'm left with a s minus z, okay, because I've distributed this s into this denominator there, and that's a ds there. Okay, so there's, and again, this has to be all over 1 over 2 pi, of 2 pi I, so there we go. So there's our two integrals. Now, clearly, we can see from the Cauchy integral formula extension that I'm going to pass this integral through then. So now what I have here then is a set of integrals, C0 of f of s, all at s to the n plus 1 ds. We know already, and there's a 1 over 2 pi there, that is equal to f to the nth derivative, all evaluated at 0, okay, divided by n factorial. Okay, so there, that anywhere I see one of these integrals, I can put that in its place. And I can see if I pass that integral in to there, if I put it there, if I scratch it out and I put that C0 there, which I certainly can do, then I've got my partial, and there's that 1 over 2 pi I that comes in. And so this whole thing then, I'm going to sneak it through here, and that becomes the sum from n equals 0 all the way to capital N plus 1 of z to the n power times the nth derivative evaluated at 0 all over n factorial. So of course this is our partial Taylor series. Okay, there we go. We've basically got it at this point. The only thing left to look at is this other term. What's this remainder bit? Okay, and we can write that down. So this is actually going to be Zn to the capital N power all over 2 pi I. Integral C0 of f of s all over s to the n power, capital N power, s minus z ds. Okay, so I'm going to actually label this. I'm going to call this, again, there's a couple parameters in here, capital N. And again, this is arbitrary. Okay, and then also z. The only conditions on z is that it's inside this disk, right? And we have this nice relationship where the modulus of z is less than the modulus of s. Okay, right? And so what we really want to do, remember this whole thing here is equal to f of z. And so what I want to do is take capital N going to infinity and then prove that rho of capital N of z always goes to 0 provided our z is interior to our contour. Okay? All right, so we need to prove that this goes to 0 as capital N goes to infinity, and capital N going to infinity means this turns into an infinite sum. And of course, this is our Taylor series. All right? And so actually what this does, this gives us an error estimate. I should say this is our error term. Well, I want to get an estimate for how big this is. And I really want to know is actually how fast it goes to 0. Because that gives me an estimate of accuracy of our finite sum. And so that's going to be interesting. So let's see if we can it's not too hard to prove that this goes to 0. We simply have to use our bounding. So what I'm going to do is take that over here. And I'm going to actually now, what we can think of is I just want to take absolute values of this thing. And so when I put the absolute values over this thing here, okay, like that, of course that becomes z to the mod z over to the capital N all over 2 pi because the modulus of I is 1. And then what I want to do is make that greater and actually pass the modulus inside the integral, which we have a theorem that we've proven before that becomes the modulus of f of s, and this becomes the modulus of s to the n power. Okay, and then finally we have the modulus of s minus z ds. Okay, so what I want to do is go further and recall then that s minus z, if I want to find a bound for this, what I really need to do is actually make this smaller. So I want to find a way to make it smaller, and we have the triangle inequality helps here, that this becomes the absolute value of s, sorry, the modulus of s minus the modulus of z, okay? So that works out like that. And of course that is going to be equal to the modulus of r0 minus r, which is simply r0 minus r, because this is a positive number here, because we already have that that r0 is greater than r. Okay, and so I can redo this again and make this even bigger still. And of course that becomes, and I can then make that r to the n all over 2 pi, and then we see we have an r naught also to the n, okay, and that's from this term right there, and that's going to move outside of the integral now because it's a constant. And then what we can do is then, because f of s lies entirely, the values of f of s are entirely found on this bounded interval, we can actually say that m, we'll call it m, m of r0 is going to be the max of the modulus of f of s, where s is on c naught. Okay, and so that'll bound f, so we can actually take that m r naught sitting there, right there, and then finally replace this denominator term with the 1 over r0 minus r, and then what we have left is an integral of c0 ds. This, of course, is just going to be 2 pi r naught. So you put it all together, and we get the following statement. The 2 pi's cancel there, and then we get r over r naught to the n power times r naught times m r naught all over r0 minus r. But the important thing to note is that that this is true. Therefore, as n goes to infinity, this goes to 0. So we've now been able to prove it. So I'm going to rewrite that on the next page to see if we can get a better picture of what's going on here. So what we have here is f of z minus the sum, infinite, or the finite sum, n equals 0 all the way to n minus 1 of the nth derivative evaluated at 0 over n factorial times z to the n power. If I take the absolute value of that, that's going to be equal to the modulus of rho n of z. Okay, and then we've proven then that that's equal. That is bounded then by this following thing: this m r naught times r naught all over r naught minus r. Okay. And then that's multiplied by r over r naught to the capital N power. So actually this gives us an estimate of accuracy for truncated sums, truncated series. And this is something the book doesn't really talk about a lot, but I actually think this is very important. The idea is that not only does this represent f, but a truncated sum, i.e. this right here with a truncated sum, actually it gets progressively better as capital N gets bigger and bigger and bigger, and that we can actually measure how far off they are using this bound. All right, so we actually have, you know, a way of measuring accuracy. So I think that's very important. All right, so now let's go over a few quick examples of some standard Taylor series. We have e to the z you can quickly check that z to the n over n factorial n equals 0 to infinity. That works. Oh, you know, I should have also noted that now let's say we want to expand. We notice that this is actually I forgot to note that in general f of z, that's going to be equal to this sum here. Okay, z to the n. But all I have to do is then define. I just have to shift z to z minus z naught in order to, and you know, I can maybe redefine my function to accommodate for that shift, and that means I can get a f of z is equal to the sum n equals 0 to infinity of f of n of evaluated at z0 n factorial z minus z0 to the n. All right, and so that is the idea is that all you have to do is perform a shift on your function, shift it by a certain amount, and then you could essentially get any function you want. So again, the function has to be analytic around z naught in order to do this. But in general, this is how you would do it. Okay, so sorry I had to take that little detour there. I wanted to clarify that point. So there's our function e to the z. And now let's try another one. Let's go with a Gaussian. What if I talk about e to the negative z squared? Well, what I can do is actually call this whole thing w, right? In which case we know that e to the w is going to be the sum n equals 0 to infinity. W to the n all over n factorial. But now we're going to say w is equal to negative z squared and put that in. And that becomes negative z squared all to the n power over n factorial. And that becomes negative 1 to the n z to the 2n all over n factorial. And so now this is how we can get other series out of an original series. We can modify our functions like this to create other series. So now let's go over one more example, that of complex log of z. So first of all, this has a domain of analyticity. So I'm going to expand about z naught is equal to 1. All right. So again, we have to draw our domain of analyticity. We know that we can't allow, so theta has to be between a negative pi and pi, and r, the modulus of the number has to be greater than 0. In general, though, if we're right here at 1, we have to expand our disk out big enough, but not too big, so that we don't start encroaching on that branch cut there. All right. So in general, our r naught has to be less than 1. Okay, in order for this to work. So what we're going to do then is, of course, so log at 1 is going to be 0. Log prime of z, that's equal to, of course, 1 over z. Log double prime of z is equal to negative z squared, 1 over z squared. Log triple prime is going to be equal to 2 z to the 3, 1 over z to the 3. Okay, and so on and so forth. What we can find is that log of z to the nth derivative, or the nth derivative, I should say, is going to be equal to n minus 1 factorial. And then we can see it alternates sign here. And that alternating sign we can write as negative 1 to the n plus 1 power. So of course, if n is equal to 1, we have a positive sign there. So that works out. And then we have to divide by z to the n, all right? But then, of course, what we always do is we evaluate at z is equal to 1. Z is equal to 1. So the coefficients here, so our f of n evaluated at z naught is going to be simply n minus 1 factorial times negative 1 to the n plus 1. Okay, so we can put that all together then, and that principal log of z is equal to the sum n equals 1, because again, I don't need that first term because it's going to be 0 anyway, so I can start at 1 instead of 0, going to infinity of n minus 1 factorial, negative 1 to the n plus 1 power, and then I put a z minus 1 because I'm expanding about z0 minus 1 to the nth power, all over n factorial. So I can rewrite this a bit. Know that n minus 1 factorial over n factorial is equal to n minus 1 times n minus 2 dot 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 all the way to 1. Likewise, we have here n times n minus 1 times n minus 2 dot 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 all the way to 1. So clearly all those cancel and we're left with just 1 over n. That means I can rewrite this as simply the sum n equals 1 to infinity of negative 1 to the n plus 1 power, all over just simply n z minus 1 to the n. Okay, all right, so there we go. There is our result. There is our Taylor series expanded for principal log expanded about n equals 1. And what we see here again is our radius that we can rely on for convergence. We need it to not overlap with that domain of non-analyticity, so we have to keep within, or have to keep within the domain of analyticity, which means that our radius has to be less than 1. So so there we have it. There's a nice result there. Okay, so thank you very much.